Hello, so in this video, we're going to differentiate the function x to the power of x. So x to the power of x, like so. Something just to bear in mind, or to bear in mind just before we calculate this derivative, is that this function, so f of x equals x to the x, is only valid for x values greater than 0. So firstly, if x was 0, then 0 to the power of 0. I mean, that's not really it's not really defined, to be honest. And then for x values less than 0, so you would get negative numbers to the power of negative numbers. So that could involve essentially complex numbers. And so we don't want that. We're only dealing with real variables and real valued functions here in these videos so far. So yeah, so this function is just defined for x greater than 0, and so yeah, we're differentiating this for x greater than 0. So to differentiate this function, it's actually going to be a similar process to how we differentiated the function 2 to the power of x. So this is like one of the earlier videos that I did on this channel. We differentiated this function 2 to the x, and the trick that we did was we said that the number 2 is just exactly the same as e to the power of ln 2. So e to the power of the natural logarithm of 2, and this is all to the power of x. You can just rewrite this just to get rid of those brackets there and multiply the powers. So you get e to the power of ln 2, so a constant, multiplied by x, like so. And then what you could do there, or what you could do now, is just use our knowledge of differentiating the exponential function and the chain rule. And when we did that calculation, we got a final answer of ln 2 multiplied by 2 to the power of x. So that was how we differentiated that function. So we're going to do a very similar thing here with this x to the power of x. Okay, so when we differentiate this, what we're going to get is, in fact, the derivative of e to the ln of x multiplied by x, like that. And then what we can do now is use the chain rule, because we've got an exponential function, and inside that exponential function, we're inserting the ln x times by x function. So this is just going to be a chain rule example. So again, just make note that we're using the chain rule, and we've done lots of examples in previous videos using the chain rule, so you can check those videos out as well. So to differentiate this, we're going to differentiate the e to the ln x multiplied by x with respect to the ln x. So with respect to the ln x multiplied by x, so i.e. with respect to the function we're substituting into this exponential function. And then we're going to multiply that by the derivative of the ln x multiplied by x, but differentiate that with respect to x. So this is just applying the chain rule. So if we just start with this first bit there, so we know that when we differentiate the exponential function of a variable with respect to that same variable, well, we just get the exponential function of that variable again. So we know that when we differentiate e to the x with respect to x, this is just e to the x by definition of, well, by one of the definitions of the exponential function. So if we differentiate it with any other variable, or let's just say a function of x with respect to some function of x, well, this is just going to be e to that function of x, again, by one of the definitions of the exponential function, or one of the equivalent definitions as well. You'll still get that same result because we proved it in, again, one of my first videos that we did. So yeah, so the first result here is going to just give us e to the ln x multiplied by x. And this second result here, so we're differentiating ln of x multiplied by x. So this is actually going to be using the product rule. So if you remember the product rule, when we differentiate with respect to x, a function multiplied by a function, I'm not going to bother writing in the variables inside the f and g function. I'm just going to leave it like that just to be brief. So when you differentiate that, so this is f dash times g plus f times g dash. And again, I'm going to be lazy and not write the f inside the x inside those functions. So yeah, that's just our product rule. And because we got the product of two functions of x and we're differentiating with respect to x, we're going to use the product rule for this second derivative over there. And if we do that, So differentiate the ln of x. Well, that's just 1 over x, because again, we did that in a previous video. So the derivative of ln of x is 1 over x. Multiply that by x, then a plus sign. So plus the derivative of x, so the g dash in this case. So again, I'll just call this f, and I'll call that g there, just to make it clear we're using this rule. So g dash is just the number 1, times by ln of x. Well, that's just ln of x, like that. And as you'll probably notice, we can just simplify this a little bit. So we get e to the ln x times by x there. In fact, we know for a fact that e to the power of ln x is just x, because the exponential function and the natural logarithm function are inverse functions. And so this is actually just x to the x. So we get x to the power of x here. Let me just move this across over here. So we get x to the x like that. And then what we get is, so 1 over x times x. That's just the number 1 because they cancel out. And then we get plus a ln x inside there. Okay, so we get our final result. So therefore, when we differentiate with respect to x, x to the power of x, this is just going to be x to the power of x, but multiplied by 1 plus the natural log of x. And that is the final result. And just to make clear, this is true for x greater than 0. The domain of this x to the x function is x greater than 0. And we can see from the result of our derivative, I mean, again, x to the x is only defined for x greater than 0, and the natural logarithm of x is only defined for x greater than 0. So that's why this is our domain of this x to the x function. And yep, that concludes this video for today.